last session, you need to go.
Yeah, I think you did. Maybe another minute or so.
Yeah.
Thank you.
Well, I need to demolish like 40 seconds. Because I added a second.
Okay. Sounds good, yes.
Yeah, this one's.
Okay, so maybe we'll begin. I'm chairing the session. I'm here from Boulder, Colorado. So we'll have, in the first session, we'll have 3 talks. And the first talk will be by A Sauls from Northwestern University.
Okay, thank you. All right, it's a pleasure to be here. Good morning, everybody. Let me begin with thanks to Pinshang and Chimao and all the organizers for inviting me to participate in this in-person workshop. And like others, it's a real pleasure.
Yeah, let me get, I'll get this was chasing us all day.
Today I'm going to discuss work with my collaborators on the chiral phase of superfluid helium-3. And this system provides some insight into transport signatures of chirality in unconventional and topological superconductors. And on that latter note, I will say a few words about the low temperature phase of uranium platinum-3. So the recent work on zero field Hall transport is with my collaborators, Alexei Shetsov, Wave Nim, Prudikorn, and Priya Sharma. But my interest in this subject has been influenced greatly by my experimental colleagues, Kimitoshi Kono and Hiroki Ikegami at RIKEN, Jivek Pia at Cornell, Bill Halpern at Northwestern, and John Saunders at Royal Holloway. In this work that I report is drawn from the reports I've listed here with my collaborators. And all the research that I've been involved in on this topic has been supported by the National Science Foundation. So chiral enantiomers are mirror reflected polyatomic molecules. They're left and right-handed versions of the molecule. So we're not advancing here. We lost our tech guy. Yeah, for the time being, I'll just do that. Okay, this is going to require using both chiralities here. Chiral enantiomers are, as I said, mirror reflected left-right versions of the same molecule, of the otherwise same molecule. Diatomic molecules, now it's working. No, sorry. I apologize here. Okay, diatomic molecules, for example, Cooper pairs of electrons or helium-3, they can break mirror symmetry and form mirror reflected partners of one another if we put them in motion in their ground state. So the wave function shown here corresponds to a Cooper pair with orbital angular momentum nu h bar. So this wave function here. The orbital motion also breaks time reversal symmetry, but the product of time reversal and mirror reflection is a symmetry, which for this talk I call chiral symmetry. A BCS condensate of these pairs with a wave function of this form are chiral superfluids, and they're the macroscopic quantum state that's either right-handed or left-handed. And these states were first discussed by Phil Anderson and Pierre Morel back in the 60s, long before the discovery of superfluid helium-3. In the case nu equal 1 is actually realized as the superfluid phase of helium-3A. And I want to tell you about why we know that.
Recording in progress.
So broken T and P symmetries can be revealed by anomalous transport, as we've heard in earlier talks. I.e. the component of the charge or a heat current is perpendicular to the applied potential or the thermal gradient. And furthermore, in this context, reverses sign if we can reverse the chirality of the ground state. So I reverse the chiral axis that I've shown here in red from L to minus L. So the Hall conductivity sigma xy and kappa xy are allowed by chiral symmetry. And the anomalous Hall effect, of course, occurs in zero field. And it's the internal motion of the Cooper pairs that's responsible for the transverse force and the transverse currents that arise. So I want to explain that as best I can in this short talk. So key message here is that anomalous Hall effects are definitive signatures of chirality. And the combination of theory and experiment can also identify the winding number, the topological Chern number, and the broken orbital symmetry of the superconducting state. And so far, I think it's correct to say that only the A phase of helium-3 is definitively identified as the chiral superfluid. It's chiral P wave with nu equal 1. So first, I want to talk about a little bit about why we believe that. But for this workshop, which is also on strongly correlated systems that drive topology, I wanted to remind a few people who may not be familiar with helium-3 that it is really a strongly correlated Fermi system. So below a few Kelvin, helium-3 it becomes a Fermi liquid with strongly renormalized interactions between fermionic quasiparticles. And this is a bit of a busy slide taken from a different talk, but what I want to emphasize here is that the quasiparticle interactions between, say, two quasiparticles with momentum p and prime on the Fermi surface, represented by this interaction function f. When we actually determine how big these interactions are, they're huge. For example, we know from sound velocity that the L equals 0 component of this interaction is roughly 100 times the Fermi energy. So in the context of what Chimal was talking about, U is about 100 times the bandwidth. The effective mass is large. And in fact, all of the interactions that we have determined from experiments are large. And I highlighted also the magnetic susceptibility, which is strongly enhanced by a factor of roughly 25. And that has, of course, led to the idea that helium-3 has a lot of ferromagnetic spin fluctuations and that they're the driver for spin triplet pairing in the system. Sorry, I did it again. There we go. I got them out of sync here. Let's see what I'm doing. There we go. So this is these are the effective interactions that have been determined by a detailed analysis of all the experimental data that we know on helium-3 in the normal state and right at TC. And what I want to emphasize is that helium-3 is not really driven, physics is not driven by the property to a Stoner instability. Actually, helium-3 appears to be governed by its nearness to a Mott transition at high pressure. So as you can see on the right panel here, the exchange interactions do show strong ferromagnetic exchange, but it's distributed over many wavelength scales. And there's also a resonance, an antiferromagnetic resonance at short wavelength scales as well. And these interactions are really responsible for the physics of the A phase. And in the context here, what I want to emphasize is that the A phase of helium-3, this chiral phase, doesn't exist in the weak coupling limit of BCS theory, even with ferromagnetic spin fluctuations.
Friction, what's the quantity of audit, both of these?
These are, the effective interaction is a density contribution, which is spin independent, and then a pure spin exchange interaction, sigma dot sigma prime. Yeah, and Q is a momentum transfer.
This is theory.
Yeah, this is, no, well, it's theory combined with experiment. So these potentials have been determined by an analysis of roughly 15 different experiments. So this is a full talk in itself. And if you want to see the version that I have presented, it's on this site here at Orlando Institute. What I wanted for this community to know is that this is really a remarkable system where you have competing interactions in the exchange channel and the density channel. So here I've shown the phase diagram, and the A phase is the chiral phase that I mentioned before. And one more time, this phase exists only by having strong correlations that lead to pairing via weak coupling theory. Weak coupling theory predicts only the isotropic B phase shown here, which is a remarkable phase in itself, but I'm talking about the chiral phase today. And in terms of its spin structure, it's an equal spin pairing state with two components of the triplet represented, and both of them are chiral. Both of them are chiral P wave. So in 3 dimensions, this is a vial superfluid with chiral fermions is existing near the nodal points. Now, we can stabilize the A phase by confining it into a film. So that's shown here as the phase diagram under confinement. This is lateral confinement into a thick film. And the scale here, 10 corresponds to roughly 1/10 of a micron film thickness. So it's still a bulk film. And this phase persists down to, for any pressure, below about 1/10 of a micron. So one goal is to dimensionally confine the system into Fermi disks, in which case we'll have a topological chiral superfluid on each Fermi disk. So in the 3-dimensional case, as I think as this community is well aware, we're going to have vial fermions, nodal excitations here in 3 dimensions. If we dimensionally confine into the quasi 2D limit, we're going to have edge fermions, all linearly dispersing. So imagine that we're all confined in a 2-dimensional film of helium-3, and somebody has the bright idea they're going to come drill a hole in your superfluid. Okay, so we're going to poke a hole in it and carve out a space. The chiral edge states then form a chiral edge current around this hole, and we can calculate the sheet current carried by those chiral edge states. It's quantized in units of h bar and the density of helium-3. We can then calculate the angular momentum, and quite remarkably, the angular momentum of this hole is the number of Cooper pairs you remove from the hole times Planck's constant. And if we move that hole from one point to another, we're going to transport that angular momentum. So the message here is that if we place an object in an impurity into helium-3, it's going to develop chiral edge states, and those edge states are going to inherit angular momentum from the chiral ground state. One of the beauties of helium-3 is that we have a natural candidate. We can take electrons and press them into the fluid, and they form a self-trapped polaron. The large zero-point energy of the electron combined with Coulomb repulsion forms a bubble of about 1.5 nanometers, and we can study the transport of the electron bubbles in helium-3. A key observation is that the large cross-section at low temperatures leads to a temperature-independent mobility in the normal state above the superfluid transition. And from that, we can determine the ionic radius of the electron. So the discovery of anomalous Hall transport Everything is going wrong again. Yes. The discovery of anomalous Hall transport of electron bubbles in the A phase by Hiroki Ikegami and Kimitoshi Kono at Riken revealed the chiral nature of helium-3. They observed both key features of anomalous Hall transport, namely the transverse current. What they did here was they set up split electrodes here with electron bubbles loaded into the film, and they drove the bubbles in the direction I'm showing here. And then they had split electrodes here to measure the deflection of the charge current. So they did these experiments with many different runs, and they could actually stabilize different chiral phases. So chiral up or down, and they could see actually the sign change of the transverse current by flipping the chirality to the ground state. The basic mechanism is we're pushing the electron bubble through a gas of these Bogoliubov quasi-particles in A phase. And when they scatter, they produce a transverse force in a perpendicular direction that is allowed by chiral symmetry. And it was Volodia-Mineyev that made this observation of this allowed anomalous Hall transport term. Alexei Shetsov and I developed a kinetic theory of these quasi-particles scattered off a moving ion when it reaches terminal velocity. And the force computed here from the differential cross-section I've shown here shows resonant scattering of quasi-particles by the addressed ion. There are 11 scattering resonances, and these resonances reflect the underlying chiral edge states bound to the electron bubble. And as you can see from the asymmetry, there's a net force in the negative y direction for a quasi-particle scattering off here, preferentially up, produces a force down on the electron bubble. Now, I want to, if you want to understand the details behind this analysis, I have to refer you to the paper, but I'm going to try and capture the basic process behind the transverse force here. So if we scatter quasi-particles in the normal state Hall an electron bubble, then it generates a drag force, the Stokes drag. And we have two species of quasi-particles. We have particles and holes that both contribute to drag. Now, in a BCS superfluid, there's an additional collision process that occurs. And I've indicated here, quasi-particle can branch convert on scattering into a hole. And when it does so, it also emits a Cooper pair into the condensate. And the reverse process also occurs, namely a quasi-hole can branch convert into a particle by absorbing a Cooper pair. Now, if the condensate is also chiral, this multiple scattering, multiple Andreev scattering that takes place forms these chiral edge states. And so we develop from the occupied negative energy states of these bound chiral fermions, we form this edge current. And this is the source of the following asymmetry in the differential cross-section. For quasi-particles, say, deflecting upward versus quasi-particles deflecting downward, it's the broken mirror symmetry that's represented here by this chiral edge state. So it's this asymmetry in the cross-section that gives rise then to the transverse force. So the net effect, of course, is that we're going to have a velocity that's not collinear with the applied force in the mean, and we represent that by the Hall angle here. So I have another problem with advancing. There we go. So this is the summary of the comparison of the theory that Alexei and I worked out for the Hall mobility of electron bubbles in the A phase. And here you see the longitudinal mobility starting from the normal state over about 2.5 decades of temperature. And then on the right-hand side, you see the tangent of the Hall angle, which is related to the ratio of these mobilities. And there are two key parameters the experimental parameters that go into this theory, TC, which is about 1 millikelvin, and the ionic radius of the electron, which we determined from the normal state mobility. And that's it. So I think it's quite a substantial Hall angle, roughly 0.3. And consider this, the magnitude of the effective field acting on an electron here at the peak of the Hall mobility corresponds to 10 to the 4th Tesla. So this is a huge effect. And coming from the interaction between the chiral fermions that are the thermal chiral fermions that are scattering off of the moving electron bubble. So,
Can you say what new purpose?
I'm sorry, yeah.
On the left there?
Yeah, I had, so it's mislabeled. This should be a parallel here. It was a switch, my mistake. So mu parallel is the mobility of the component of the velocity along the electric field, in plane electric field. So the usual drag mobility. I did it again.
But it's, sorry, so it gets enhanced in the superconducting state because you get.
Okay, yes, that's a very good question. So what Leo's asking about is why does the drag mobility increase by 2 orders of magnitude as we go below TC? 2 effects. One is you get resonant forward scattering in the superfluid state. That's about half of the effect. The other half of the effect is you open up a gap and you suppress the number of thermal excitations. So the gap is not perfect. And that's why we actually get power laws at low temperature for the mobilities. If I plot the temperature dependence of the mobilities themselves, then they go as T to the power 3 and T to the power 4.
You say it's not perfect, I mean, they're nodes.
Yes, linear nodes. Good. So in summary, electrons are dressed by a spectrum of chiral fermions. Electrons are left-handed in a right-handed vacuum. And they acquire an angular momentum of roughly 100 h-bar. And the Riken experiments, which observe this Hall effect in the A phase, originates from these 2 broken symmetries and the topology of the A phase. So what happens if we want to look at the electronic analog? So now we have impurities are not mobile, well, typically not mobile in a solid, so we have fixed impurities. What we need to do is invert the process and move the thermal excitations through the fixed impurities. So that's going to generate, of course, multiple scattering off of this fixed set of impurities is going to produce a heat diffusion. And if we have a chiral superconductor present, then the same mechanisms, I did it again, sorry. We have the same mechanism, branch conversion scattering, chiral edge state formation, and skew scattering is at work and generates an anomalous thermal Hall effect. So basically, an extension of this theory to the electronic case here is what Wavenem, Prudicorn, and I have worked out for, a mean density of impurities in a chiral superconductor. Now, anomalous thermal Hall effects are not new. Theoretical predictions of these effects in topological superconductors dates at least to, I think, Reed and Green in 2000, with extensions to wild superconductors by Paul Goswami and Nevedomsky. Here I'm talking about an effect which is related through symmetry and topology, but it's not equivalent. This is edge physics, and this is bulk physics if we have a bulk density of impurities. So here are some results on the longitudinal and Hall conductivities for a chiral P wave and a chiral D wave superconductor. And I think the highlights here is that the longitudinal conductance is really insensitive to the impurity ionic radius or the winding number. But by contrast, the Hall term is quite sensitive to both the symmetry and topology. So KXY is also suppressed if you compare it to the longitudinal conductivity as measured at TC. So here you see the characteristic signature and the temperature dependence of branch conversion scattering, linear onset peak at intermediate temperatures, and then a decay depending upon the nature of the gap of the superconductor. So another comparison that's useful is to compare the bulk Hall effect from impurities versus the edge term. So here's your comparison for, say, a fairly conservative estimate on a superconductor with KF psi naught about 50. The Hall terms, the impurity terms generally dominate by a couple of orders of magnitude. You have to get to the ultra clean limit in order to expose the edge contribution.
So, yeah, I have a question. So this is for a two-dimensional, like 2D gap?
It's not, yeah, so 2D refers to the fact that we have an open Fermi surface. So it was modeled on the gamma band of strontium ruthenate, where we would have nearly cylindrical band. And so it has no vial points for the superconductor.
So I mean, if it's fully gapped, why wouldn't you have Anderson crystallization of, the presence of a lot of impurities?
Well, we're not anywhere near that density of impurities. So we're in the limit also where the characteristic transport mean free path is large compared with the coherence length. So Anderson localization is when transport mean free path is over the Fermi wavelength. So we're in many ways, but this is an important point because these are unconventional superconductors, non-magnetic impurities can destroy the superconducting state. So here, that's why I've taken a very conservative value of the transport mean free path, which converts into a density of impurities. Here you still have a robust TC of a chiral superconductor. But you have a large anomalous Hall contribution, even with this level of density of impurities, large compared with each contribution. Does that help? Yeah, so no, these are different radius, ionic radius of the impurity shown here. So this is a two-dimensional case where we did 2D chiral P wave or chiral D wave, and our impurities then have an ionic radius, which is the disk radius. So this is the hard disk impurity value KFR. So, a lot of studies, you're always in the limit where you have point impurities, and point impurities give rise to a Hall effect only for a chiral P wave. You can't activate the transverse force if you have only S wave scattering off the impurity. Yes, please.
It will become XY normalized temperature, right? You know, normalized temperature TC.
Yeah, so I wanted to scale. So I took the scale of the edge contribution, but evaluated at TC, just to give you an order of magnitude of how big these effects were. Okay. So that's one of the messages here, is that you really have to work hard to get an ultra clean sample in order to expose the edge term. Right? So it can be done at ultra low temperatures if you can produce, even with impurities present, if you can avoid having a finite density of states at the Fermi level. But then you have to get down to temperatures below the bandwidth of that impurity band in order to again expose the edge contribution. And then since it's scaling linear in temperature, it's just getting smaller and smaller. So it's not easy. I'm sorry for that. Yes, please.
Yeah, so just to make sure I understand, maybe you just answered this. So this bulk quantity, is it coming from thermally excited polyparticles across the superconducting gap, or is it coming from polyparticle states that are brought down by impurity? Yeah.
Yeah, good question. So if I go to low temperatures, it's the latter. I still have thermal excitations above. If I have a finite density of states that extends over some region of energy, and I get my temperature down below that edge, then I have thermal excitations even at low energy and those contribute to both the longitudinal and the transverse. At higher temperatures, it's dominated by this is a 2D case. If I have a nodal case, which is next slide. Then I have a lot of thermal excitations coming from the filter. And it's the wind of those excitations scattering off of the pre-normalized impurities, the dominant effect. So, well, let me show you that. If I can keep from screwing up my presentation. Okay, I didn't. I'll show you the 3D case at the end. So I'll just end with some comments on where to look for these impurity-induced anomalous Hall effects. And one of my candidates would be to look in the B phase of uranium platinum 3. How many minutes do I have, Leo? None?
Basically.
Okay, all right. So let me just flip through and just say one thing is that this phase, the uranium platinum 3 and multiple superconducting phases, and this B phase is predicted theoretically to break time reversal and mirror symmetry. And so there's evidence that that is indeed the case from polar Kerr effect. It's a surface probe, optical surface probe. It's very convincing. It would be really nice to have a bulk test. And so that's what my final message here is that if anomalous thermal Hall effect would confirm broken P symmetry in the low temperature B phase. But there are a number of other examples where this type of bulk transport probe might be useful for convincing the community that we've discovered chiral superconductor. Thank you very much.
How important is the mirror symmetry to observe the anomalous electrical and the thermal Hall effect?
In superconductor.
Yeah.
Yeah, it's essential.
So if you just had the broken time reversal symmetry, you wouldn't see this effect, or?
No, I don't think so. No, but it's what do you have in mind? How are you going to break time reversal symmetry?
Well, I think it means D plus IT.
Yeah. So
That's how you break mirror symmetry. Yeah. Take a plane in the Z plane and reflect. This one. Okay, take a plane. Let's reflect in the ZX plane. Right, so then we're going to change P y to minus y. So the state changes from, say, px plus IPy squared to p minus IPy squared.
but what about S plus IS, for example? Is that the same?
No, I don't think so. I don't see a mirror plane.
I see. So for S plus IS, you wouldn't observe the anomalous Hall effect.
So S plus IS, you mean you'd have to have two bands.
Sure.
So you have an S wave on one band, S wave on another band, and you're going to have a mechanism to correlate their phase at pi 2.
Sure.
Okay, I don't know. I somehow doubt it, but I don't have a specific.
Jim, for the I have a question just to clarify from the first part of your talk where you talk about the helium-3. Do I get correct the qualitative picture that the reason you get anomalous Hall, like if I look at the final expression, it looks like a Lorentz force, but in the presence of this fictitious field, and if you ask, well, what is the magnitude of B effective? It's proportional to R squared, the size of your hole, and that's because essentially that's how many, that's what's an effective orbital moment is carried by that hole put in helium-3, right? And then, but how do I understand this? The magnitude of the field is proportional to this orbital momentum itself. So it's a how should I say, self-interaction effect. The larger the hole, the larger the effective field it feels.
Yeah, so the transverse force scale to transport cross section, but it's modified by the fact that in order to get the transverse force, you have to have branch convergence. And that's where the angular momentum is transferred between the scattering and excitation. So you have to have angular momentum transfer from the condensate, from the condensate to the quasi-particle wind that's scattering off of excitation. It's that angle momentum transfer that gives you the transverse force, and that the amount of Andreev scattering you get scales as delta of T over TC quantity squared. That's why you get a linear onset that increases TC. So the effective cross-section for this effect here is the transport cross-section scattering R squared, but then modified by the branch conversion.
I see. So what you call branch, sorry, I'm not familiar with the term, but branch conversion is what you just explained. Is this a fact that scales with delta squared?
Yes.
I see.
Yeah,
Thanks.
and that figure where you see linear onset peak and then drop at low temperature, classic signature of branch conversion.
I see. And the same might happen in superconductors. So is that
Yeah.
specific to helium-3
So that's why
physics?
you see these figures that I showed for the chiral D wave, also on setting linear peak around 0.8, 0.6, depends on the material.
Okay. A question here. Okay, so when you break this mirror and the time reversal, why you have a single domain? Why you have a single chiral domain?
Yeah.
So mock case, this mock case, so you get nice signal, but these days people can do space resolve, the scanning in a mock. So are you sure it's a really single domain?
Yeah, so I didn't show it, but I would love to, I can show you afterwards, but Ono and Ikigami did many different runs. They saw single domains, they saw multiple domains. They could see micro earthquakes, tremors, switch domains. They actually followed the domain motion. And they could trigger a complete change in the chirality using mechanical techniques. Earthquake.
Okay, I'm afraid we have to move on, so maybe save questions for coffee break. Let's take.
Yeah, okay. So I need to